Hey folks, this is the first of two videos about how we represent covalent compounds and the bonding within those, where we're talking about Lewis structures. A Lewis structure shows us how atoms are connected and how the electrons are being shared within a covalent compound. They're the pictures that you've probably seen that look kind of like, well, this. This is the Lewis structure for water. Again, it's just showing me how the atoms are attached and where we have pairs, where we have electrons that are not involved in bonding in addition to the ones that are involved in bonding. So let's break this down a little bit. As I look at this picture, what I'm showing is that I have a hydrogen atom and that there is a pair of electrons, I'm going to draw it out here, shared between the hydrogen atom and the oxygen atom. So that's here, and our Lewis structures will represent those with a line. Same thing is true on the other side, where I have my electrons being shared. These are our bonding electrons, or our bonding pairs. But you'll also notice in my left-hand structure, I had some dots that were kind of just hanging out on the oxygen, but not between any individual atom. These electrons are electrons that are localized just on that single atom, on that oxygen atom. And these we call our non-bonding pairs, or our lone pairs of electrons. We're going to find over time that there's a ton of information we can tease out of this Lewis structure, so you need to figure out how to draw these. I strongly encourage you to use the Nab method when it comes time to draw Lewis structures. There's different ways people do it. This one I have found is the most foolproof. So what the Nab method stands for is you're going to figure out how many needed electrons you have. And when I say needed, that would be the number of electrons required to provide a full valence shell, so 8 electrons for every atom in your molecule. Well, 8 electrons for most things. We'll come back to that. Then you're going to calculate the number of available valence electrons. Remember, only those outer electrons are involved in bonding, so they're the only ones we're going to count. And then we need to figure out how many bonds are required. Let me show you how this works. Okay, to find the number of needed electrons, we're going to count our total target number. And I mentioned here that for most atoms, this is 8 as the target, because remember you have to have a full S and P shell to have a full valence shell. So that's 2 for the S, 6 for the P, total of 8 electrons. There's a couple of exceptions. The most important exception is hydrogen. Hydrogen only needs 2 electrons to fill its valence shell. Its electron configuration is 1s1. The 1s orbital can only take 2 electrons, so it needs 2 electrons to fill that valence shell because it's on that first period. A couple other exceptions you'll come across fairly commonly. Aluminum and boron actually only need 6. That tends to be their stable number. We'll talk about why in class, but just be aware that those are some exceptions to the 8 rule. So let's see how this works. This first part with the molecule ammonia, which is NH3. So for ammonia, if I'm going to figure out how many electrons are needed, I have 1 nitrogen that needs 8 electrons. So I'll do 8 plus. I have 3 hydrogens, each which need 2. So 3 times 2 is 6. And so I need 14 electrons to fill the valence of all of these atoms if I were just to fill them independently. That's the first step. Available. You're going to count the number of valence electrons you have. S and P electrons total in your atoms. How do you do this? Well, you look at the periodic table. Remember, that periodic table reflects our electron filling. And so everything in the first column here, group 1, those have 1 valence electron because they're 1s1, 2s1, 3s1, whatever. Everything in the second column, those have 2 valence electrons. Skip the middle, still skip the middle. Everything in the third column gets 3, 4, 5, 6, 7, 8. So you're just going to count from left to right to count the number of valence electrons you have. Again, this ties back into those orbital filling diagrams. So for counting our total, when I go to look at my number of available electrons, nitrogen, being in group 15, has 5 valence electrons. 5 plus 3 hydrogens, each which have 1 valence electron. So this gives me a grand total of 8. So I have 8 electrons available. Okay, how does this relate to the number of bonds? We have to share electrons to make those number of available electrons match the needed. So there's a nice sweet little formula to figure this out. You're going to take the number of needed electrons, subtract the number of available electrons, divide by 2. And that will calculate the number of bonds that your molecule has. So in this case, my number of bonds will be 14 minus 8 divided by 2. That's 6 divided by 2. That is 3. So I know that I'm going to have 3 bonds in this molecule. Okay, once you've done the NAB, you're ready to start drawing. You will put, generally speaking, the element that is different from the others in the middle. Formally, it is the the least electronegative element. We'll talk about what that is in class. So for what we're working with right now, the one that's different. Nitrogen goes in the middle. I will arrange my 3 hydrogens around it. And then I know I need to have 3 bonds holding it together. Well, I only have 3 atoms, so I have to put 1 bond to each of those atoms. You're not quite done yet because I've only used 2, 4, 6 electrons. Remember, each bond is 2 electrons. You have 8. The other 2 have to go somewhere. Well, they're going to allow us to fill the valence for all of our atoms. So you're going to check atom by atom, starting from the outside, working in, to see if you've completed the valence shell or filled the valence shell with the target number of electrons. Hydrogen's target is 2. This hydrogen has 2 electrons around it because of this bond right here. So that corresponds to 2 electrons. Hydrogen set. All of my hydrogens have 2 electrons around them due to that 1 bond. So hydrogen is good. Check out the nitrogen. The nitrogen has 2, 4, 6 electrons around it because it has the 3 bonds. That's not 8, which is its target. So I need to add my last 2 electrons as a lone pair to the nitrogen. This uses all of the available electrons and gives 8 electrons, a full valence shell, to that central nitrogen. Which means that this, let me erase my little commentary stuff here, is my completed Lewis structure for NH3, which is commonly known as ammonia. Let's take a look at 2 more examples, and then we're going to do a bunch in class, of course. Okay, let's look at CS2 and HCN. For CS2, when I get ready to start nabbing things, needed, carbon needs 8. I have 2 sulfurs that each need 8. This is 24 electrons needed. Available. Carbon is in the 4th, or has 4 valence electrons. 1, 2, skip the middle, 3, 4. Carbon has 4 valence electrons. Each of those sulfurs has 6, so 2 times 6. This gives me a grand total of 16 electrons. So when I figure out how many bonds I need, I'll take 24 minus 16 divided by 2. This is 4 bonds. 4 bonds, you say. Well, let's start drawing. Carbon goes in the middle because it's different. Put your sulfurs on either side. I have 4 bonds. As much as you can, especially when you've got this much symmetry, distribute your bonds symmetrically. 1, 2, 3, 4. Okay, this is good. Now I need to check to fill the valence shells of all of my atoms, starting from the outside, working in by using lone pairs. My sulfur over here has 2 4 electrons around it right now due to those bonds. So its target is 8, so I'm going to add 2 lone pairs. Now I've got 2, 4, 6, 8 electrons around that sulfur. I'll do the same thing on the other side. Symmetry is good. And now I have used 2, 4, 6, 8, 10, 12, 14, 16 electrons. That's how many I have, which is perfect, but check to make sure that you've filled carbon's valence. Carbon wanted 8. It has 2, 4, 6, 8 electrons around it because of those 4 bonds. So there's your Lewis structure for CS2, carbon disulfide. Last example I want to do right now, HCN. Okay, here we go again. Let's start nabbing. Needed, I have a hydrogen. Hydrogen needs 2. Carbon needs 8. Nitrogen needs 8. That is a total of 18 electrons needed. Available, hydrogen's in my first group. It only has 1 valence electron. Carbon has 4. Nitrogen has 5. So I have 10 electrons. So my bonds, 18 minus 10 divided by 2 is 4. I get 4 bonds once again. So I draw this. In this case, I'm going to draw it in the order that it's listed. Carbon is my central atom. Now I need to start putting my 4 bonds in. This molecule is not symmetrical. Don't get overly enthusiastic with going 2 bonds on each side. I'm going to put 1 bond to hydrogen and stop there, because hydrogen will only ever form 1 bond because I've filled its valence. It's set. So leave that. Let's put the other 3 bonds between the carbon and the nitrogen. And at this point, I have filled hydrogen's valence. If I look at my nitrogen, it has 2, 4, 6 electrons from those 3 bonds, and so it needs another pair of electrons on the end. Carbon has 1, 2, 3, 4 pairs, so a total of 8 electrons, which is its target. And I have used, always check this at the end, 2, 4, 6, 8, 10. I have used 10 electrons in my Lewis structure, which matches my number of available electrons. So it's good. I want to give you just a couple of kind of general reminders. Hydrogen only ever forms 1 bond. That fills its valence shell. Never, 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 please never give hydrogen more than 1 bond. Not going to happen. Other things that I want you to be aware of is that your fluorine will also only ever form 1 bond. We'll talk more about this in class. But basically, fluorine is really small and it has a relatively high nuclear charge. And so it's not very good about sharing electrons. So it'll share 1 pair of electrons, but it's not going to share additional electrons beyond it. And perhaps the most important thing, at the end of drawing your Lewis structures, count to make sure you have the proper number of electrons used.